If our protons rotated around in sync, in phase, and nothing changed, then we'd get a signal as illustrated in the previous section. This, however, is not what happens. This is the situation right after the RF pulse was switched on. As soon as the RF pulse is switched off, the whole system, which was disturbed by the RF pulse, goes back to its original, quiet, peaceful state. It relaxes. The newly established transverse magnetization starts to disappear, a process called transversal relaxation. And the longitudinal magnetization grows back to its original size, a process called longitudinal relaxation. Why is that? The reason why the longitudinal magnetization grows back to its normal size is easier to explain, so let's start with that. No proton walks on its hands longer than it has to. A sort of human trait. The protons that were lifted onto a higher energy level by the RF pulse go back to their lower energy level and start to walk on their feet again. Let's have a closer look at what happens. Sending in the RF pulse makes, let's say, 3 protons walk on their hands. Note that for simplicity, the protons were not depicted as being in phase. This subject is covered in more detail in sections 12 and 16. After the RF pulse is switched off, protons go back to the lower state of energy. In other words, point up again. But not all protons do this at exactly the same time. Instead, it is a continuous process, as if one proton after the other goes back to its original state. The effect is that longitudinal magnetization increases and grows back to its original value. What happens to the energy which they'd picked up from the RF pulse? The energy is just handed over to their surroundings, the so-called lattice. And this is why this process is not only called longitudinal relaxation, but also spin lattice relaxation. If you plot longitudinal magnetization versus time after the RF pulse is switched off, you get a curve like this one. It increases with time. This curve is also called a T1 curve. The time that it takes for the longitudinal magnetization to recover, to go back to its original value, is described by the longitudinal relaxation time, also called T1. This actually is not the exact time it takes, but a time constant, describing how fast this process goes. This is like taking time for a circuit at a car race. The time gives you an idea of how long the race may take, but not the exact time. Or more scientifically, T1 is a time constant comparable to the time constants that, for example, describe radioactive decay. That T1 is the longitudinal relaxation time can easily be remembered. If you turn the 1 upside down, it looks very much like an L, as in longitudinal, reminding you also that it describes the spin lattice relaxation. But there are more hidden hints to this. The 1 also looks like a match, and this match should remind you of something which we've also mentioned already. Longitudinal relaxation has something to do with exchange of energy, thermal energy. which the protons emit to the surrounding lattice while returning to their lower state of energy. Enough of the longitudinal magnetization. What happens with the transversal magnetization? Let us assume that this is the situation just before the RF pulse is switched off. When the RF pulse is switched off, the protons get out of step, out of phase again, as nobody is telling them to stay in step. For the sake of simplicity, this has been illustrated for a group of protons which all point up. Let us have a look at what happens one more time. Before the RF pulse is switched off, a transversal magnetization has been established. When the RF pulse is switched off, the protons get out of step, fan out. Thus, the transversal magnetization decreases. When you look at these dephasing proton ensembles from the top, it becomes obvious how they fan out. Being in phase in the first place, then losing phase coherence, pointing less and less in the same direction. We heard earlier that protons precess with a frequency which is determined by the magnetic field strength that they are in. And all the protons should experience the same magnetic field. This, however, is not the case. Firstly, the field of the MR magnet in which the patient is placed is not totally uniform, not totally homogeneous, but varies a little, thus causing different precession frequencies. And, secondly, each proton is influenced by the small magnetic fields from neighbouring nuclei that are also not distributed evenly, thus causing different precession frequencies too. These internal magnetic field variations are somehow characteristic of a tissue. Now let us return to our previous illustration. After the RF pulse is switched off, the protons are no longer forced to stay in step. And as they have different precession frequencies, as we've just learned, they'll soon be out of phase. It is interesting to see how fast the protons get out of phase. Just suppose that one proton, P1, is rotating at 10 million revolutions per second. In other words, with a precessing frequency of 10 MHz. Due to inhomogeneities, a neighbouring proton, P2, is in a magnetic field which is 1% stronger. This proton has a precession frequency of 10.1 MHz, 1% more. In 5 microseconds, P2 will have made 50.5 turns or revolutions, while proton P1 will have made only 50. So, in this short time span, the protons will be 180 degrees out of phase, cancelling their magnetic moments in the respective plane. Similar to what we did for the longitudinal magnetization, we can plot transversal magnetization versus time. What we get is a curve like this one. This curve is going downhill, as transversal magnetization disappears with time. And as you probably expect, there is also a time constant, describing how fast transversal magnetization vanishes, goes downhill. This time constant is the transversal relaxation time, T2. How to remember what T2 is? Easy. T2 is T times 2 is double T is TT. and this means it describes the T transversal, thus the relaxation of the transversal magnetization. The resulting curve is thus called a T2 curve. Another term for transversal relaxation is spin-spin relaxation, reminding us of the underlying mechanism, a spin-spin interaction. How to remember which one is the T1 and which one the T2 curve? Just put both curves together. You can see something like a mountain with a ski slope. You first have to climb to the top, T1 curve, before you can ski down, T2 curve. It takes longer to climb a mountain than to ski down, which helps us to remember that T1 is normally longer than T2. So, time for a review. We have learned that protons are like little magnets. In an external magnetic field, they align parallel or antiparallel. The lower energy state, parallel, is preferred. So a few more protons align this way. The protons perform a motion that resembles the wobbling of a spinning top. This motion is called precession. The precession frequency is dependent on the strength of the external magnetic field, a relationship which is described by the Larmor equation. The stronger the magnetic field, the higher the precession frequency. Protons, pointing in opposite directions, cancel each other's magnetic effects in the respective directions. As there are more protons aligned parallel to the external field, there is a net magnetic moment aligned with or longitudinal to the external magnetic field. A radio frequency pulse that has the same frequency as the precessing protons can cause resonance, transfer energy to the protons. This results in more protons being antiparallel and thus neutralizing or cancelling more protons in the opposite direction. Consequence? The longitudinal magnetization decreases. The RF pulse also causes the protons to precess in sync, in phase. This results in a new magnetic vector, the transversal magnetization, which moves around with the precessing protons. When the RF pulse is switched off, transversal magnetization decreases and disappears, while longitudinal magnetization increases again. This longitudinal relaxation is described by a time constant T1, the longitudinal relaxation time. The transversal relaxation is described by a time constant T2, the transversal relaxation time. Longitudinal and transversal relaxation are different, independent processes, and that's why we discuss them individually. That's what you should know by now. At the end of our last section, we already learned that it takes longer to climb a mountain than to ski down it, which means that T1 is normally longer than T2. Just to give you an idea, T1 is about 2 to 10 times as long as T2. Or in absolute terms in biological tissues, T1 is about 300 to 2000 milliseconds, and T2 is about 30 to 150 milliseconds. It is difficult to pinpoint the end of the longitudinal and transversal relaxation exactly. Thus, T1 and T2 were not defined as the time when relaxation is complete. Instead, T1 was defined as the time when about 63% of the original longitudinal magnetization is reached. T2 is the time when transversal magnetization decreased to 37% of the original value. These percentages are derived from mathematical equation, but we do not want to go into more detail here. However, we should mention that 1 over T1 is also called longitudinal relaxation rate, and 1 over T2 transversal relaxation rate. Previously, it was believed that measuring the relaxation times would give tissue characteristic results, and thus enable exact tissue typing. This, however, proved to be wrong, as there is quite an overlap of time ranges. What is a long, what is a short relaxation time, and which tissues have long or short relaxation times? When you go to your favorite bar, which is naturally crowded, as it's a popular place, and order a long drink representing water, you have to wait quite a while to get your drink. T1 is long. When you finally have your long drink, it also takes you a long time to drink it. So, T2 is also long. And we want to remember, water, liquids have a long T1 and a long T2. As water has a long T1 and a long T2, it is easy to imagine that watery tissues, tissues with a high water content, can also have long relaxation times. Interestingly enough, pathological, diseased tissues often have a higher water content than the surrounding normal tissues. Now, look at this gentleman getting a hamburger. These normally contain much fat and will represent fat for us. The hamburger is fast food. You get it fast. Thus, fat has a short T1. What about T2? It takes some time to eat fast food, fat. However, you normally spend more time with your long drink. So, fat has a shorter T2 than water. Actually, T1 depends on tissue composition, structure, and surroundings. As we have learned, T1 relaxation has something to do with the exchange of thermal energy, which is handed over from the protons to the surroundings, the lattice. The precessing protons have a magnetic field that constantly changes directions, that constantly fluctuates according to the Larmor frequency. The lattice also has its own magnetic fields. The protons now want to hand energy over to the lattice to relax. This can be done very effectively when the fluctuations of the magnetic fields in the lattice occur with a frequency that is near the Larmor frequency. When the lattice consists of pure liquid, water, it is difficult for the protons to get rid of their energy, as the small water molecules move too rapidly. And as the protons, which are on the higher energy level, cannot hand their energy over to the lattice quickly, they will only slowly go back to their lower energy level, their longitudinal alignment. Thus, it takes a long time for the longitudinal magnetization to show up again. And this means that liquids, water, have long T1s. When the lattice consists of medium-sized molecules, most body tissues can be looked at as liquids containing various sized molecules, kind of like a soup, that move and have fluctuating magnetic fields near the Larmor frequency of the precessing protons. Energy can be transferred much faster. Thus, T1 is short. This can again be illustrated by our hamburger and race car example. Handing over hamburgers, in other words, energy, from one car, proton, to the other, lattice, is easy and efficient when both move with the same speed. With a difference in speed, the energy transfer will be less efficient. Why does fat have a short T1? The carbon bonds at the ends of the fatty acids have frequencies near the Larmor frequency, thus resulting in effective energy transfer. And why is T1 longer in stronger magnetic fields? As we heard at the beginning, the precession frequency depends on magnetic field strength, a relationship described by the Larmor equation. If we have a stronger magnetic field, then the protons precess faster. And when they precess faster, they have more problems handing down their energy to a lattice with more slowly fluctuating magnetic fields. What influences T2? T2 relaxation comes about when protons get out of phase, which, as we already know, has two causes: inhomogeneities of the external magnetic field and inhomogeneities of the local magnetic fields within the tissues. As water molecules move around very fast, their local magnetic fields fluctuate fast and therefore kind of average each other out. So there are no big net differences in internal magnetic fields from place to place. And if there are no big differences in magnetic field strength within a tissue, the protons stay in step for a long time before they dephase. And so T2 is longer. With impure liquids, for example, those containing some larger molecules, there are bigger variations in the local magnetic fields. The larger molecules do not move around as fast, so their local magnetic fields do not cancel each other out as much. These larger differences in local magnetic fields consequently cause larger differences in precessing frequencies. Thus, protons get out of phase faster. T2 is shorter. This can be illustrated by the following example. Imagine that you drive down a street with many potholes. When you drive slowly, which is equal to the surroundings moving slowly, and you are standing still, your car will be bumping up and down as it drives over each pothole. The differences in the surroundings, the magnetic field variations, influence you considerably. When you drive very fast, which is the same as if the surroundings move very fast, you do not feel each single pothole anymore. Before they have a major effect on you, you are already back at normal street level. Thus, their effect is averaged out. You are much less influenced by differences in the surroundings, the variations in magnetic field strength. What does all this have to do with what we want to know? All these processes influence how your MR picture will finally look. A brief review might be advisable. T1 is longer than T2. T1 varies with the magnetic field strength. In stronger magnetic fields, it is longer. Water has a long T1. Fat has a short T1. T2 of water is longer than the T2 of impure liquids containing larger molecules. Now let us perform an experiment. Here you can see two protons, precessing around the z-axis. I hope that you can recall that the z-axis indicates the direction of a magnetic field line. Instead of only these two protons, in reality there may be 8 pointing up and 6 pointing down, or 82 up and 80 down. There should only be 2 more protons pointing up. As we know, these are the ones that have a net magnetic effect, because their effects are not cancelled out. Now let us send in an RF pulse, which has just the correct strength and duration, so that one of the 2 protons picks up energy to go into a higher state of energy. In other words, points down, walks on its hands. What will happen? To find out, just activate the RF pulse by clicking on it. To find out, just activate the RF pulse by clicking on it. Just activate the RF pulse by clicking on it. The longitudinal magnetization, up to now resulting from 2 protons pointing up, will decrease. In our example, to 0. 1 pointing up is neutralized by 1 pointing down. But, as both protons are in phase, there is a new transversal magnetization which had not been there before. Try to imagine tilting a longitudinal magnetic vector 90 degrees to the side. Let's repeat that. The RF pulse tilts the longitudinal magnetic vector 90 degrees to the side. Such an RF pulse is called a 90-degree pulse. Naturally, other RF pulses are also possible and are named accordingly. For example, 180-degree pulse. To really understand this, let us look at another example. Here we have 6 protons pointing up. We send in an RF pulse, which lifts 3 of them onto a higher energy level. The result? We no longer have a longitudinal, but a transversal magnetization, again having used a 90-degree pulse. What happens when the RF pulse is switched off? To find out, try clicking it off. Two things happen. Protons go back to their lower state of energy, and they lose phase coherence. It's important to note that both processes occur simultaneously and independently. For the sake of simplicity, let us look at what happens step by step, and first focus on the longitudinal magnetization. After the RF pulse is switched off, one proton goes back to the lower energy state, resulting in 4 protons pointing up and 2 pointing down. The net effect? We now have a longitudinal magnetization of 2. Then the next proton goes back up. Now 5 protons are pointing up and 1 down, resulting in a net longitudinal magnetization of 4. After the next proton goes up, longitudinal magnetization equals 6. You have surely already noticed that the transversal magnetization decreases at the same time. Why is that? You should be able to answer this. After the RF pulse is switched off, the precessing protons lose phase coherence. Let us now leave out the little red arrows, each of them representing a single proton, and focus on the sum vector. When the RF pulse is sent in, the longitudinal magnetic vector is tilted 90 degrees to the side. As we already know, this vector moves corresponding to the precessing protons. But for the sake of simplicity, we'll leave out the motion. After the RF pulse is switched off, the transversal vector decreases, while the longitudinal vector increases. As you remember, vectors represent forces of a certain size and a certain direction. If you add up vectors pointing to different directions, you will come up with a direction that is somewhere in between, depending on the amount of force in the original directions. If we do the same with the longitudinal and the transversal vector, we get the sum vector. This sum vector is very important, as it represents the total magnetic moment of a tissue in general, and thus can be used instead of the 2 single vectors, representing longitudinal and transversal magnetization separately. Our magnetic sum vector, during relaxation, goes back to a longitudinal direction, in the end equaling the longitudinal magnetization. What we have to remember is that this whole system is actually precessing, including the sum magnetic vector. And thus, after the RF pulse is switched off, the sum vector will actually perform a spiraling motion. By switching the RF pulse on again, you can start this animation over and over again. I hope that you recall that a changing magnetic force, moment, can induce an electric current, which is the signal that we receive and use in MR. So if we put up an antenna somewhere in our last example, we will get a signal like this one. This is easy to imagine if you think of the antenna as a microphone and the sum magnetic vector as having some kind of a sound-emitting device like a steam pipe at its tip. The further the vector goes away from the microphone, the less loud the sound. The frequency of the sound, however, remains the same, because the sum vector spins with the precessing frequency. So the signal from our experiment disappears with time, however, has a constant frequency. This type of signal is called a free induction decay signal, or FID signal. By now, it should be obvious that the magnetic vectors directly determine the MRI signal and signal intensity by inducing electric currents in the antenna. Instead of the terms longitudinal or transversal magnetization, we can also use the term signal or signal intensity at the axis of our T1 and T2 curves. This will hopefully become clearer as you continue with this program.